once again, you are welcome to this last class for this semester. And I believe that the journey so far, it was not easy, I know. It's a sacrifice, and some of us put in the best. I know a couple of you guys are here that from day one, you never miss a day. And I want to say kudos to you guys. It's all about encouragement. Let me share the screen. And in this case now, I will just, it's the last chapter. And if you look at it, go and check the books. We actually touch each of the chapters one way or the other. I'll pick example, I'll solve it. And although initially some people believe that I should be reading from books to books, of which I quickly explain the way it works. And some people that can cope, they started following the class, and today it's another story. So if you look at this, these are the things we did last week. You can see all like this. It doesn't make any, you don't need to bother yourself. Go and check the definitions of every, if I were you, by now I will be writing all the definition out the way I did in the examples. You can see that some of the material are not well arranged here. So that's why I didn't bother myself projecting this all the time. Look at this last chapter, is the characteristics of minimum polynomial. This we are to look into Cayley-Hamilton theorem. What does it say? Cayley-Hamilton problem is very simple. It's just talking about this thing. Every square matrix satisfies its characteristic equation. Every square matrix satisfies its characteristic equation. What is a square matrix? A square matrix of order n by n, same number of rows and column. A square matrix can be 2 by 2, 3 by 3, 4 by 4, 8 by 8, 9 by 9. It depends, but the number of rows must equal to number of columns. That is a square matrix. Then, in a situation whereby we are talking about characteristics equation, we all know characteristics equation. These are the things I explained to us last week, whereby we have what we call a matrix A minus lambda identity equals to 0. I will write it on the board. You will see it very soon. It's what is called a characteristic equation. And this case, where your A is a given matrix and your lambda is a scalar and your I is identity matrix. So there are proof on that where that leads to the zero matrix. So a zero matrix in the sense that we just want to show us that, okay, this particular matrix, Hamilton, it's all about how do you prove that this is equals to zero matrix. So you can see, I will show us the way we use polynomial. It's just a simple theorem and a simple proof. Then from then it leads us to inverse of a matrix. As you can see from here, they said the determinants, the adjoints, they multiply the both of them together. Adjoint of a matrix, as we all know, multiplied by identity, and at the end of the day, it gave us this. So if you can have this of order 0, what next do we need to do? I will only lay emphasis on how to solve it in your own custody, in your own way of things, where anytime you have a chance. But I want you to check this remark, the remark I'm showing us here. Please, if you have your pen and paper, you can write these two remarks down because we are going to work with it. He said f of t is equals to determinants into, you can say a minus t or ti minus a, which is, or f of a equals to determinant of ai minus A, which is the same thing as determinant of A minus A, which is the same thing as determinant of 0 at equals to 0. That is, what we are saying is, you must prove the Cayley, how to verify the Cayley-Hamilton is when you prove that your determinant is equals to 0. You show that the matrix is equals to 0. I'm going to verify some, and you will all see the way I will verify them. And same thing happened here in their own example. We want to verify that a squared minus 3a plus 2i, this is I, not 1, that is identity matrix, equals to 0. And here we have a squared. A squared means a multiplied by a, which is equals to this. Then substitute a multiplied by a into this equation, and you already have a already. Put a inside this place. Then you have, it must equal, you must show that it equals to 0. If it's not equals to 0, that means it is not true. It does not mean you are not right. Don't make mistakes. It shows that the Cayley-Hamilton theorem is true in this case. But in case you do not have 0, 0, 0, 0, it simply means it is not true. That is, you cannot, Cayley-Hamilton in this case, it is not true. Examiner can want to test you. At what point? They can ask simple question. At what point is Cayley-Hamilton is true? When the matrix all equals to, when you have 0 matrix, that is when it's true. But when you are not having a 0 matrix, it is not true. So please take note of that. Don't say, oh, Dr. Oke said this. No, be careful. Is that okay? So let me stop sharing this one. We'll still come back to it. And let me share this. Let me share our board. Can you see the board now?
Yes, sir.
Okay. Okay. This is not really the one. I use this one for another class. But I think I can still, okay, it's the same, sorry. It's the same board. I want to be sure. So let's look at the definition as I explained now. And let's see how many of us were able to solve the assignment that I gave you last week. Please raise up your hand. If you are able to solve it, you will got my mail. Or if you don't get my mail, that means I didn't see your work. Okay, I believe you got the mail. Okay, let's look at this. For Cayley-Hamilton, the statement there says, Cayley-Hamilton theorem. Please, can you see my screen?
Yes, sir.
Okay,
yes, sir.
Thank you. Thank you. Okay, I still have some here. Let me just start from the back. Cayley-Hamilton theorem. What is the characteristics? This is theorem. Let me write it in full. So for Cayley-Hamilton theorem, like I said, it says, the statement says this. Let's look at the statement that says this. It says, every square matrix satisfy its characteristics. Equation. So the first thing is, what is square matrix and what is characteristics equation? You need to check the two. What is square matrix? What is characteristics equation? In this case, our square matrix can be we all know the square matrix because we are using it here. It's a matrix of order square of order n by n. Same number of rows and columns. So you can see same number of rows and column. Then if you say characteristics, what is characteristics? Let's look at it. Characteristics equation, let me put it this way. It's just a mathematical definition. It's going to be A. Do you remember this? That is determinant of A minus lambda I equals to 0. That is what they call characteristics equation. Characteristics equation is this. It is called characteristics equations, where we can call A tends to given matrix, and our lambda is also tends to scalar. You remember last week. Then our I is tends to identity matrix. Identity matrix. So, any question?
Sir, please, can you fully adjust your screen so that we can see the board?
Oh.
All right, thank you, sir.
You're welcome. So, any question? If there's no question, I will need to ask you. Let me stop this. Yes, Idris.
Sorry, I supposed to have dropped my hands when you asked for those that did the assignment. I forgot.
Oh,
Sorry,
okay.
sir.
I think maybe I'll be collecting some things. I'll be giving you penalty once you raise up your hand and you do not lower it. There will be a penalty for that. Okay, let's continue. So in this case now, do I need to show us? Okay, let me show us. Let me quickly just show us what we are trying to solve in this case. It's just a very simple thing, but a bit technical, which I will advise. Let your focus just be on what we are doing in this case now. Let's just manage the screen this way for now. Okay, in the proof, we have the proof, but I will just explain the proof in a simple manner. It said, let A be a square matrix of order n. Its characteristics, let me use this one. Its characteristics equation, A minus lambda I is equals to 0. Remember, according to what we did last week, if you are not in the last class, please go and watch the video. After we have something of this nature, especially the characteristics equation, what we normally do at this point is it will lead us to polynomial. It's either by order 2 or order 3. So we will now want to project those polynomial. We want to say polynomial naught, P naught plus P1, that is of order 0. If you now have order 1, you have lambda 1, plus P2. If you have order 2, that is, you have raised to power 2, plus P3. If you have P3, you have order 3, that is, you have raised to power 3, plus Pn minus 1, which is multiplied by lambda n minus 1, and plus Pn lambda n, all equals to 0. Remember, we started from 0. It simply means at this point, our n is equals to 1. Our n is equals to 1 at this point. What this 0 means is you have 1 minus 1, and lambda also 1 minus 1. That's the meaning. Meaning n minus 1 will be what? P0, and lambda, anything raised to the power 0 is what? 1. So we have P0 multiplied by 1, which is equals to P0. That is why you are seeing this one. That's why we said n minus 1, because if you generalize it in series time, you will see n minus 1. So like that. I'm just using this one to explain. That's not our focus. So don't say, where do you see n minus 1? So when you now put it in general term, it simply means you have n, always deduct 1 from the n. So it will lead us to this one. So where our P0, comma P1, comma P2, like that, till Pn minus 1, comma Pn are scalar, are scalar. So we have to prove that, don't forget, in this case now, P0, anywhere you see P0, P0 multiplied by, don't forget, I just explained something. I said P0 multiplied by 1. Our 1 is identity. We call it identity matrix in this case. Multiplied by identity plus P1 multiplied by A. Our lambda now has turned to A, where lambda is equals to A. So just take note of that. Plus P2 A squared plus P3 A cubed plus Pn minus 1 An minus 1 plus Pn An, everything equals to 0. This everything equals to what? 0. We call it 0 matrix. Now, what this thing is telling us, if you want to find the inverse of it, all you need to do is just to multiply your determinant multiplied by identity. But I don't want to bother us. If you want to see the full detail of the proof, is in your notes. You can take your time and look at it. But let's look at the example. What are the things the examiner can ask us? They can ask us, example, which I'm going to give us here. Example 1 says, verify, we can ask to verify Cayley-Hamilton. They can give you simple matrix theorem from the matrix. A equals to 1 minus 6 minus 1 minus 2. And find its inverse. They can ask us to find its inverse too. How do we do it? Remember, I asked us to write the the step down the other time. The first step is just to find the determinant, find the characteristics, and the last one is to check whether it's equals to 0. So for us to do it, solution now will be, what is the matrix? The matrix A is this 1 minus 6 minus 1 minus 2. That is our matrix. Then we should check the characteristics. Characteristic equation is what? We know A, determinant of A minus lambda I equals to 0. So in this case now, we need to first of all check the lambda I. For us to check the lambda I, we have, that is, you have lambda. What is the dimension of, what is the order of this matrix? Somebody should tell us.
It's 2 by 2.
It's 2 by 2, thank you. 2 by 2. Is it a square matrix or not square matrix, please?
It's a square matrix.
It's square matrix.
It's a square matrix.
Yes,
Now,
sir.
it's a square matrix, that is the number of row. We have row 1 and row 2. We have column 1 and column 2. They are equal.
Yes, sir.
Just mute yourself, please. So the number of row equals to number of column. No, now we can now multiply. What? This is identity. Identity you must form must also be 2 by 2. You can't form 3 by 3 because you want to impress anybody. No, it must be equivalent to the question you are given. Please take note. If you are given 2 by 2, the identity matrix must also be 2 by 2. If you are given 3 by 3, the identity matrix must be 3 by 3. So I hope I'm clear. And what is identity matrix? Somebody should tell us, please. Simple definition for identity matrix. John Oko, tell us.
Yes, sir. An identity matrix is a matrix whose diagonal is 1 and other element is 0.
Simple. That's just it. So we have 1, 0, 0, 1. That's all. Your diagonal must be equal to 0. Must equal to 1 rather. So you have this. Now multiply your identity by your lambda. So you have it to be lambda 0, 0, lambda. That's all. So let's go to A. The equation says we must first of all, for us to have A minus lambda I, meaning we must have A. Our A is what? 1 minus 1 minus 6 minus 2. Everything minus lambda 0, 0, lambda. Any question? So at the end of the day, you have it to be, remember it's a determinant they asked us to find here. It is determinant sign. So which is 1 minus lambda minus 1, because minus 1 minus 0 is minus 1. So the next is minus 6. This is minus 2 minus lambda. Everything equals to 0. Any question at this point? Do we have question? Raise up your hand before we move forward. Remember, the question says we should verify the Cayley-Hamilton theorem. Cayley-Hamilton theorem will give us 0 matrix. That's just it. And if it cannot give you 0 matrix, it simply means it is not true at that point. The examiner can ask you at what point Cayley-Hamilton theorem is true. at the point whereby you have zero matrix, or at the point whereby you don't have, please take notes. So we can proceed by saying, now let's solve this one. This multiplied by this, right? Minus this. So I can say I have 1 minus lambda multiplied by minus 2 minus lambda. Then minus 1, we have minus already. Minus 1 multiplied by minus is plus 6 equals to 0. If you open the bracket, you have minus 1 times 1 multiplied by minus 2 minus lambda, then plus 2 lambda, then plus lambda square. Everything minus 6 equals to 0. So we can order it accordingly. Lambda squared minus lambda plus 2 lambda plus lambda minus 2 minus 6 minus 8 equals to 0. We can call this one equation 1. Let's say equation 1. So according to by Cayley-Hamilton, by Cayley-Hamilton theorem, lambda equals to A. By Cayley-Hamilton theorem, lambda equals to A. So meaning that anywhere I see lambda in my equation, I will equals it to be A. So I can go ahead by saying A squared plus A minus 8 equals to 0. So, but don't forget, when you have a constant at the Cayley-Hamilton, you multiply the constant by identity matrix. Let's go back from the theorem. Look at this. From our theorem here, what happened? This is a constant. They multiply that constant by an identity. So the same thing will happen to 8. We multiply the 8 with I identity. So somebody will now ask you, where do you see I? You can see where we see the I. We already cover ourselves by saying by Cayley-Hamilton theorem. So let's call this one equation 2. So we can proceed, but for us to proceed, we need to get what is A squared. Our A squared is the same thing as A multiplied by A. That is A dot A, which is the same thing as, what is our A initially? 1 minus 1 minus 6 minus 2. Then we have another A, 1 minus 1 minus 6 minus 2. So everybody, let's calculate it. What do you have? Calculate A minus A, please. A minus A is what? Are they coming bright? What is A minus A? A multiplied by A. A multiplied by A. Regina. Kristana. Bashir. So Olaide, A multiplied by A. You don't need to run away. Some people are running away already. Any problem? Any question? If you have the answer, raise up your hand. A multiplied by A. These are the things we've done. It's just multiplication. Okay, Musa, what's the answer?
It's 71610.
Oh, that's for you. Let's wait for other person. Okay, really one.
Sir, it is 71610.
Okay, let's wait for another person. Okay, A multiplied by A is simple. That is row multiplied by column. So here we have John Oko. John.
Yes, sir. Yes, sir. It is 71610, sir.
Okay, 1 multiplied by 1. Let's quickly do it because of the others. 1 multiplied by 1, 1 multiplied by 1 plus minus 1 multiplied by minus 6. So that is it. Then you pick another one, another row. Okay, you multiply this one again to the another column. You have it to be 1 multiplied by minus 1 plus minus 1 multiplied by minus 2. Don't just assume people knows it. You will just be shocked that this place, some people will not be able to continue because of this place. So then you pick other one, minus 6 multiplied by 1 plus minus 2 multiplied by minus 6. Okay, then minus 6 multiplied by minus 1 plus minus 2 multiplied by minus 2. So at the end of the day, we can just do the solution here. Minus 1 times 1, 1 times 1, 1, plus, minus times minus plus, 1 multiplied by 6 equals to 7. Here you have minus 1, minus times minus plus, 1 times 2 plus 2 equals to 1. Here you have minus 6 plus 12 equals to 6. Here you have minus times minus plus 6 plus 4 equals to 10. So you can, at the end of the day, you have it to be 7, 1, 6, 10. I believe it's clear to everybody now. How did they get it? You can see the way we got it. So let's continue. That is our A squared. Your A squared is equals to this. So we can proceed. Now, equation 2 becomes remember equation 2. Equation 2 says A squared plus A plus 8 multiplied by identity. Everything must equal to 0. That is the meaning. If it's not equal to 0, it simply means the rule of engagement is not old at that point. So we have it to be a squared plus a plus 2 minus 8i equals to 0. So let's put a square here. Our a square is 7, 1, 6, 10 plus a. Our normal a is what? 1 minus 1 minus 6 minus 2 minus, we all know 8 multiplied by identity is 2 by 2 is going to be 8, 0, 0, 8. So everything equals to 0. How do we solve it? So it's simple. Just take them accordingly, according to the identity. Pick 7 first. 7 minus 7 plus 1, the sign that is in between them, then minus 8. That's the first one. The second element, you pick this one, will be 1 minus 1 minus 0. Don't forget. Then the next one is 6 minus 6 minus 0. The next one is 10 minus 2 minus 8. So what is the answer, please? Anybody?
0.
The first one is what?
The first one is 0.
0. The next one is?
0.
And the last one?
0.
Now, therefore, Cayley-Hamilton theorem is true at this point. That is the meaning. I will call it CH, but CH theorem. In this case. So in another case, it might not be true. Don't forget, not all the time. Like I told you, in another case, it might not be true. But now, in the last, they now ask us to find its inverse. Find its inverse. How do we find inverse? Okay, for inverse, what you need to do, you consider recall equation 2. Recall equation 2. So our equation 2 is what? You pick equation 2 to be, and okay, recall equation 2 and multiply it by A inverse. We all know A inverse. So therefore, and in this case now, when you have A inverse, it simply be A multiplied by A inverse. I'm just giving us an int. It's the same thing as identity. That is, when you say A multiplied by 1 all over A, this one cancel this, right? Is equal to 1, and the 1 here is identity. So that's the meaning. So you need to take note. Then we have A squared from plus A minus 8i. Minus 8i, everything multiplied by identity. So when you multiply them by identity, you equate to 0. So what do you have here? So if I have A squared multiplied by identity plus A dot identity minus 8i dot identity. So Here, this cancel this. This cancel this, remain identity. And here, 1 multiplied by this is A inverse. So we have here A plus I minus 8 inverse. Everything equals to 0. So don't forget what we know identity. We know this. We are asked to calculate this.
Excuse sir.
Go ahead.
That 8. Why did you remove the identity there?
I just use, remember identity in this case is like 1, multiply it by A inverse, we give you A inverse.
Okay. Okay.
That is what I did. That is just like I multiply by identity, A inverse.
I understand.
Will now
Thank
be
you,
A inverse. You are welcome. So it will now be, we are looking for 8 of this. So how do we now solve this? It will be A inverse equals to A plus I. You know, when you take A inverse, negative A inverse to the other side, it will be like this. Do you agree with me? So remember, we are looking for A inverse. So how do we solve A inverse? Make A inverse subject of formula. So you have 1 all over 8 in brackets A plus I.
Okay. Hello, sir.
Go ahead.
Please come back where you wrote this A inverse equals to A plus I. How did you come about this?
A inverse equals to A plus I. Where? Here.
Yes,
Okay,
sir.
it's very okay. Wait. I only jump a step. Okay, let me close. Let me.
Okay.
Don't worry.
All right.
Don't worry. Don't worry. Now, is it clear? Let me clean the board. Now, are we okay with this?
Yes, sir.
Please, I want you to unmute yourself if you are okay. Are you okay with this?
Yes, sir.
Yes,
Can
sir.
I
Yes, sir.
proceed from here?
Yes, sir.
Okay.
Yes, you can proceed, sir.
Okay. Now, from here, remember everything equals to 0.
Yes.
Now, this is negative. Take it to the other side. I have A plus I equals to 8A inverse. Please mute yourself. So now I want to make A, remember we have to find A inverse. It's the same thing as writing A equals to A plus I. Do you agree? Now, if I want to make A inverse subject of formula, remember it's the one I'm looking for. So I can now say A inverse is the same thing as 1 all over 8. If I divide both sides by 1 all over 8 in A inverse, excuse me, plus I. I know A, I know I. I can substitute them. I can say 1 all over 8, a big bracket. Let me just use a big bracket and put my A matrix here. My A matrix is 1 minus 1 minus 6 minus 2 plus identity matrix of the corresponding matrix. So if I can solve this one, it will equals to my A inverse. That's just what we are saying. So Now, for us to solve this, we can add them together. It is very simple. So 1 plus 1, 2. Minus 1 plus 0, minus 1.
Minus 1.
Minus 6 plus 0.
Minus 6.
Minus 2 plus 1.
1.
Really?
Minus
Minus
2
2 plus 1.
Minus 1.
This is what we call your E inverse. That is what they ask you to calculate. Any question? That is how you show in Cayley-Hamilton method theorem, you verify your matrix and you verify your inverse. Can I stop sharing?
Hello, sir.
Yes, any question?
Yes, the first example we did, we have proved that Cayley-Hamilton is equal to 0. Now we are dealing with the inverse. How am I going to be sure that this is the right answer in terms of dealing with the inverse?
Don't make mistakes. I'm not saying because it is true is the right answer. I'm only saying it confirms the establishment of the theorem.
Okay.
Not that you must get 0, 0. I just give you one question now. For example, if I'm setting the question, I can ask you, at what point Cayley-Hamilton is not true? Just a multiple choice question. I can ask you that question. If you know Cayley-Hamilton, you will know that when all the matrix is not equal to 0, when you don't have 0 matrix, Cayley-Hamilton is not true. But when you have 0 matrix, Cayley-Hamilton is true. Simple. Does not mean it's not right. You are just to prove that, oh, Cayley-Hamilton is true anytime I have 0 matrix.
Yes, I understand that one you are saying. My problem
Now,
is the inverse.
the question now says, if you do it right, okay, how do you know that I pronounce your name very well, Musa? How? Is there any law to that?
No, sir.
Aha. Now, the law in this case is very simple. They told us we are to find inverse. If you can obey simple law, this thing is very simple. It's not something that is, look at this highlighter now. If you can obey this law, if you can remember that this is equals to this, if you can also show that this is equals to this, first thing, you must know that anytime you multiply A multiplied by A inverse, it will give you identity matrix. You are right. Are you getting it?
Yes, sir.
If you can know that anytime you multiply identity matrix, multiply by A inverse, it will give you this. You are right. Then substitute it. Apply it here. And make your A inverse subject of formula. The rest thing you get will be A inverse. It's like normal equation that we normally do. You make something subject of formula and you calculate the rest. That's what I did. Yes, Joshua. Joshua, you raise up your hand.
So can I
Joshua.
still ask?
Okay, ask question.
I want to also ask question on that theorem because there's something I saw on that theorem that I really did not understand. Please, can we go to the theorem? The final answer on the theorem.
Okay, yeah.
No, the theorem. Yes, very good. When you were proving the lambda, when we say P naught plus P1 lambda plus P2 lambda square, blah, blah, you are going like that. Then you now came to the second one, you now say P naught I plus P1A. I thought the A should start generating from P naught A raised to power 0 before P naught A raised to power 1 and continues like that.
The law says this, that anytime you have constants, multiply it with identity matrix.
Then before you now start with A again.
You now remember A, the law has already told us that we should make A to be equals to lambda. And here we have lambda. Then we start with A. Anywhere you see lambda represented by A.
Yes, sir.
And anywhere you see constant, multiply it by identity. Remember, when you see at the end of the day, when you prove here, we got to a point, we have 8. It's the same law. Look at what we did here. We substituted here. Anywhere you see lambda, we put what? A squared plus A. Are you getting it? Then,
yes, sir.
When we now got the P, this is P naught, our own P naught in this case, we multiply with the identity matrix. That's why I said, take your time, go and read. I don't want to bug you with theorems. That's why I just pick example to explain the theorems. At your own leisure time, please read all the definitions there and it will make more sense to you.
Okay,
Any
thank
other?
you, sir.
Joshua, what are you writing? You are raising up your hand, you are dropping it. I hope you are okay now. Any question? Joshua, you raise up your hand.
Yes, sir. Sorry.
Yes.
I
What's the question?
In that this thing, before we get the final answer.
I can't hear you very well.
Sir, can you hear me now?
Yes, you are breaking, but we'll manage it.
I said we'll get the final answer.
Yes.
You cancelled A squared multiplied by A raised to power minus 1. Then, I don't know if you can share the board. Let me just show you what I was trying to.
Yeah.
Hey, just scroll down. Keep scrolling.
At this point.
No, to the last this thing. Hey, it's okay.
I've been not cancelled. Look at it. You have A square divided by, okay, don't let me say divided. Let me multiply by A raised to power minus 1.
Yes.
Is that not? According to the law of indices, what will happen? You have A 2 minus 1. Am I right?
Yes, sir.
Which is going to be what? A.
Yes.
Raised to power 1, which is the same thing as A. That is what I did.
Okay.
Because, okay, go ahead.
And then that line before the last highlights, you canceled A multiplied by A raised to power minus 1, and you put a I as that's the identity.
Yes, because it's 1.
Okay.
because you are going to have A multiplied by 1 all over A. Is that not?
Yes.
Remember, somebody will ask, where do you see 1 all over A? It's very simple. Anytime you have S raised to power minus 1 is the same thing as 1 all over S. It's the same thing as A raised to power minus 1 is the same thing as 1 all over A. That's
Okay.
just what I did.
Okay, sir.
So this one cancel this. You have 1. And the 1 is cannot stand alone, returns to what? Identity.
Okay. Thank you, sir.
You're welcome. Any other question? So it will turn to identity. So from there, and I explain at this point, when you have 8i multiplied by a minus this, it will definitely, I multiplied by this, it just turns to 8 multiplied by a inverse. It's just like 1 multiplied by this will give you a inverse. Please take notes.
Sir,
Yes. Any other question? Kosi, you said you can't hear me. Can you hear me now? Oh, I'm just hearing that now. Francis Izuchukwu, why are you just coming?
Sir, I've been having a bad network, very poor connection. Good morning, sir.
Oh, good morning. So sorry. You can check the video. We check the video. We are trying to. Tiami Oluwaseun. Am I right?
Yes, sir.
Oh,
Good morning,
okay.
sir.
Good morning. Is it your first time in this class?
Yes, sir.
Oh, that's interesting. When you hear that we are closing today, you are just coming now, or you are just seeing the announcement today for the first time.
I just saw it today for the first time.
Today for the first time. Okay.